Deep in southern Africa, a wall of concrete stands between life and catastrophe. 128 meters tall, 579 meters long, holding back more than 180 billion cubic meters of water. Enough water to create the largest man-made reservoir on Earth by volume. Enough water to power entire cities, entire industries, even 2 nations. For more than 6 decades, the Kariba Dam has been one of humanity's greatest engineering achievements. A symbol of ambition, a symbol of progress, a symbol of power. But beneath that massive structure, something is going wrong. Not on the surface, not where tourists can see it, not where satellites can easily detect it. Deep below the dam, water has been quietly carving a giant hole into the bedrock. Year after year, decade after decade, growing larger, growing deeper. Today, that erosion pit has reached a depth of more than 90 meters, deeper than engineers originally believed possible, and still growing. If the rock beneath the dam loses its ability to support the structure, the consequences could extend across 3 countries. Entire communities could find themselves directly in the path of a catastrophic flood wave. Millions of people live downstream. Millions depend on Kariba every single day. And yet, the most dangerous threat facing this dam isn't visible from above. It's hidden beneath the water, hidden beneath the concrete, hidden beneath decades of assumptions. So how did one of the most celebrated engineering projects in African history become the focus of international concern? And what exactly is happening beneath the world's largest man-made lake? Because this story doesn't begin with a crack. It begins with a mystery hidden underwater. Chapter 1. The Hidden Hole Beneath Kariba. If you stand on top of Kariba Dam today, nothing looks wrong. The concrete wall still rises above the Zambezi River. The turbines still generate electricity. The reservoir still stretches beyond the horizon. To most people, Kariba looks exactly the way it has for decades. Stable, powerful, permanent. But appearances can be deceptive, because the most dangerous threat facing this dam isn't visible from above. It's hidden hundreds of feet below the surface. And it began with something engineers thought they understood: water. Every year, especially during heavy rains, Kariba must release enormous volumes of water through its spillway gates. When those gates open, millions of tons of water plunge downward at extraordinary speed. The impact is violent. The force is immense. And for decades, that force has been striking the riverbed directly below the dam. Engineers knew erosion would occur. In fact, they planned for it. The basin beneath the spillways was designed to become what engineers call a plunge pool, a sacrificial area where flowing water could dissipate its energy safely. According to the original calculations, the plunge pool would eventually stabilize at around 30 meters deep. That was the expectation. That was the model. That was the assumption. Reality had other plans. Over the years, the river refused to cooperate. Instead of stabilizing, the plunge pool continued growing, deeper, wider, more aggressive. Survey after survey revealed the same disturbing pattern. The erosion wasn't slowing down, it was accelerating. Then came one of the most alarming discoveries in the dam's history. When engineers conducted detailed underwater surveys, they found the plunge pool had reached depths exceeding 80 meters. Later inspections suggested sections approaching or exceeding 90 meters, 3 times deeper than what the dam's designers originally anticipated. Imagine digging a hole nearly as deep as the Statue of Liberty is tall, then placing one of the world's most important dams beside it. That is essentially the situation engineers are dealing with today. And depth isn't the only problem. As the plunge pool expands, it moves closer to the dam's foundation, closer to the point where concrete meets rock, closer to the place where the entire structure transfers its weight into the earth below. For decades, the erosion remained largely invisible to the public. Tourists taking photographs couldn't see it. People living downstream didn't know it existed. Even many residents who depended on Kariba's electricity had never heard of the plunge pool. But inside engineering circles, concern was growing. Because once erosion reaches critical foundation zones, the conversation changes. It is no longer about maintenance. It becomes a question of structural survival. The frightening part is that nobody can simply look at the dam and know exactly how much risk exists beneath the water. The battle is happening out of sight, inside fractured rock, inside hidden cavities, inside a landscape that engineers can only map through sonar scans, sensors, and underwater inspections. Then came another discovery. The plunge pool wasn't the only thing changing beneath Kariba. The foundation itself was beginning to reveal secrets that nobody expected. And those secrets would raise an even more troubling question. What if the rock beneath the dam was never as stable as people believe? Engineers expected the plunge pool to stop growing decades ago. It never did. But the hole itself wasn't the most disturbing discovery. Because when investigators looked beneath Kariba's foundation, they found evidence that the rock supporting Africa's most important dam might not be as stable as anyone once believed. To understand how that became possible, we have to go back to the beginning. Chapter 2. The dam that changed Africa. Long before engineers were worrying about erosion, long before sonar scans and structural monitoring systems, long before anyone questioned the future of Kariba, there was only one question. Could it even be built? To understand why Kariba matters today, you have to understand what it represented in the 1950s. At the time, much of southern Africa looked very different. The region was growing, industry was expanding, demand for electricity was exploding, and one river seemed to hold the answer. The Zambezi, the fourth longest river in Africa, a river powerful enough to shape landscapes, powerful enough to flood entire valleys, and, if engineers could control it, powerful enough to transform a continent. The location chosen for the project was a remote gorge straddling what are now Zambia and Zimbabwe. Steep cliffs, extreme heat, seasonal floods, virtually no infrastructure. Many experts believed constructing a giant dam there would be impossible. Others called it reckless. But in 1955, construction began anyway. What followed became one of the most ambitious engineering projects Africa had ever seen. Thousands of workers poured into the gorge. Roads had to be carved into the cliffs. Equipment had to be transported into terrain where almost nothing existed. Every ton of concrete, every machine, every worker had to battle geography before they could battle the river. Then, nature struck back. In 1957, massive floods tore through the construction site. Water surged through the gorge with such force that workers were swept away. Dozens lost their lives. Construction was thrown into chaos. For a moment, it appeared the river might win. But the project survived, and the work continued, day after day, month after month, year after year. More than 1 million cubic meters of concrete were eventually poured into the structure, creating something extraordinary. A double curvature concrete arch dam, one of the most sophisticated dam designs ever attempted. Instead of resisting the water with sheer mass alone, Kariba used its curved shape to transfer enormous forces into the canyon walls on either side. It was elegant, efficient, and revolutionary. When the final sections were completed in 1959, the world took notice. Kariba stood 128 meters tall, 579 meters across, a giant concrete wall rising from the heart of Africa. Behind it, a new inland sea began to form, Lake Kariba, stretching nearly 280 kilometers, covering thousands of square kilometers, holding more water than any other man-made reservoir on Earth. For many, it was proof that humanity could conquer nature, a monument to engineering, a symbol of progress, a triumph over the river that had once seemed untamable. But as the waters rose behind the dam, not everyone saw it as a triumph, because while governments celebrated, tens of thousands of people were about to lose everything.
As Lake Kariba continued to rise, entire villages began disappearing beneath the water. Homes vanished, farmland vanished, sacred sites vanished, and for more than 57,000 people, the greatest engineering triumph in Africa was about to become a personal disaster. Chapter 3. The Human Flood. When most people think about dams, they think about concrete, turbines, electricity, engineering. But before Kariba became a lake, it was home. Long before there were power stations, there were villages. Long before there were transmission lines, there were farms. Long before there was a reservoir stretching across the horizon, there was a river valley filled with people. For generations, the Tonga people lived along the Zambezi River. The river was not simply water. It was their food, their transportation, their culture, their identity, their history. Everything revolved around it. Then the dam arrived, and everything changed. As construction progressed through the late 1950s, government officials began preparing for a consequence they had known was coming from the beginning. The valley would disappear. Once the floodgates closed, the water would rise, and it would keep rising. Village after village received the same message: leave. More than 57,000 Tonga people would eventually be displaced. Entire communities uprooted, entire ways of life erased. Families were forced to abandon homes their ancestors had occupied for centuries. Fields were left behind. Burial grounds were left behind. Sacred sites disappeared beneath the rising water. Many residents were promised new land, new opportunities, a better future. Reality often looked very different. The new settlements were frequently located on poorer land. The soil was less productive. Access to the river was gone. Fishing traditions collapsed. Agricultural yields fell. Poverty increased. Decades later, many researchers would describe the resettlement program as one of the most disruptive forced relocations in modern African history. And yet, while thousands of people were struggling to rebuild their lives, another rescue operation was making headlines around the world. As the waters rose, wildlife became trapped on shrinking islands. Elephants, antelope, lions, snakes, animals stranded by the growing reservoir. The response became known as Operation Noah. Teams traveled across the flood zone, rescuing thousands of animals before they drowned. The images captured international attention. Photographs appeared in newspapers around the world. For many people, Operation Noah became one of the most famous conservation stories in African history. And it was extraordinary, but it also revealed a difficult contrast. The world watched the rescue of animals. Far fewer people paid attention to the human beings losing their homes. For the Tonga people, the rising waters never truly stopped. Because displacement is not a single event, it is something that echoes through generations. Even today, descendants of those communities continue to debate whether the benefits of Kariba ever justified the cost. And while the social wounds were still healing, something unexpected was beginning to happen beneath the lake itself. Something the engineers had never predicted. The water was becoming so heavy, it appeared to be changing the earth beneath it. At first, nobody connected the earthquakes to the lake. Then the tremors kept coming, again and again and again. What scientists discovered next would challenge one of the fundamental assumptions behind the entire project. Chapter 4. Can a dam create its own earthquakes? When Kariba Dam was completed in 1959, engineers believed they had solved one of Africa's greatest engineering challenges. The river had been controlled, the turbines were operating, the reservoir was filling, everything appeared to be working exactly as planned. Then the ground started shaking. At first, nobody was alarmed. Small tremors are not unusual in many parts of the world. Most were barely noticeable. But as the years passed, the earthquakes kept coming. Again, and again, and again. Scientists began noticing a strange pattern. The timing of the earthquakes seemed connected to the filling of Lake Kariba. The larger the reservoir became, the more seismic activity appeared in the surrounding region. This raised a disturbing possibility. What if the lake itself was triggering the earthquakes? Today, scientists call this phenomenon reservoir-induced seismicity. The concept sounds almost unbelievable. A man-made lake becomes so massive, so heavy, that it alters the stress conditions deep underground. Lake Kariba contains roughly 180 billion cubic meters of water when near full capacity. That is an almost unimaginable weight pressing down on the Earth's crust. Water also seeps into existing fractures in the rock. As pressure increases inside those fractures, faults that were once stable can begin to move. The result? Earthquakes. Not theoretical earthquakes, real earthquakes. In the years following the filling of Lake Kariba, more than 20 earthquakes exceeding magnitude 5 were recorded in the region. Some scientists believe Kariba became one of the most significant examples of reservoir-induced seismicity ever documented. To be clear, this does not mean the dam is causing every earthquake, nor does it mean a catastrophic earthquake is inevitable. But it does mean that one of the key assumptions made during the original design process was incomplete. The geology beneath Kariba was not as simple as engineers once believed, and that wasn't the only surprise waiting inside the structure. As researchers continued studying the dam, another concern began attracting attention: the concrete itself. Because while the public worried about the rock beneath the dam, some engineers were becoming increasingly interested in what was happening inside the dam. Microscopic chemical reactions, slow, invisible, relentless, processes capable of changing concrete from within. Not over months, not over years, but over decades. And by the early 2000s, signs of those changes were becoming impossible to ignore. The growing hole beneath Kariba was alarming. The earthquakes were unexpected, but neither was the reason engineers installed more than 200 sensors throughout the dam. Those sensors were watching something else. Something happening inside the concrete itself. Chapter 5. The Race to Save Kariba. By the early 2010s, the warnings could no longer be ignored. Engineers had spent years studying Kariba. They had mapped the plunge pool, monitored the concrete, tracked the seismic activity, and the conclusion was becoming increasingly difficult to avoid. The dam was not in immediate danger of collapse, but the risks were growing, and time was no longer on their side. In 2014, an international coalition stepped in. The World Bank, the African Development Bank, the European Investment Bank, and several international partners. Together, they approved one of the largest rehabilitation programs in the dam's history, nearly $300 million, not to build a new dam, not to increase power production, but simply to preserve what already existed. The plan focused on two critical objectives. The first was the spillway gates. For decades, those gates had endured enormous hydraulic forces. If they failed during a major flood event, the consequences could be severe. The second objective was even more urgent: stop the plunge pool, stop the erosion, stop the hole from moving any closer to the foundation. On paper, the solution seemed straightforward. Reshape the plunge pool, reinforce vulnerable areas, control how water strikes the riverbed, slow the destructive process. But reality beneath Kariba was far more complicated. As construction teams entered the gorge and began detailed excavation work, they discovered conditions far different from what earlier models had predicted. The rock was more fractured, more irregular, more damaged. The deeper engineers looked, the more uncertainty they found. Schedules slipped, costs increased, deadlines moved. What was supposed to be a relatively straightforward rehabilitation project became a long and difficult engineering battle. Meanwhile, the river never stopped working. Every rainy season brought more water. Every discharge event brought more erosion. Every delay gave nature more time. Then came another challenge: climate change. Throughout the 21st century, Southern Africa experienced increasingly unpredictable rainfall patterns. Some years brought devastating droughts. Others brought intense flooding. In 2016, water levels in Lake Kariba fell to roughly 12% of capacity. Power generation dropped dramatically. Rolling blackouts spread across Zambia and Zimbabwe. For millions of people, the crisis was no longer theoretical. The dam was not only becoming harder to protect, it was becoming harder to operate. Kariba had entered a new reality. Too little water created problems. Too much water created problems. And every decision carried consequences: release water and increase erosion, hold water and increase pressure, generate electricity and stress aging infrastructure, reduce generation and risk economic disruption. The margin for error was shrinking. By the early 2020s, rehabilitation work was still underway. Progress had been made. The spillway modernization advanced. Major engineering works continued inside the gorge. But one uncomfortable fact remained: the clock had not stopped. Some inspections continued to detect active erosion beneath the dam. Monitoring systems remained active around the clock. More than 200 sensors continued feeding data to engineers every day, watching, measuring, waiting. Because despite decades of research, despite international funding, despite some of the best engineering expertise available, nobody could simply declare victory. Kariba was still standing. But the battle was not over. And there was one final question that nobody wanted to answer. What would happen if they ran out of time? Engineers don't expect Kariba to fail tomorrow. They don't expect it next week or next month. But every emergency plan begins with the same question. Not when the dam succeeds, but when the dam doesn't. And that raises one final scenario. A scenario nobody wants to see. What happens if Kariba fails? Chapter 6. What happens if Kariba fails? For more than 60 years, Kariba Dam has done exactly what it was designed to do: hold back the river, generate electricity, support millions of lives. Most days, people downstream never think about it. They wake up, go to work, send their children to school, turn on the lights, and trust that the massive wall of concrete upstream will continue doing its job. But every major dam in the world has one thing in common. Engineers do not only study how it operates, they also study how it could fail. Not because failure is expected, but because the consequences are too large to ignore. For Kariba, the worst-case scenario begins with a loss of structural stability. Not necessarily a dramatic explosion, not a Hollywood-style collapse, but a progressive failure somewhere within the foundation system. A process that could accelerate rapidly once critical support zones are compromised. If that happened, billions of cubic meters of water would begin moving downstream. And the geography below Kariba makes the situation especially dangerous. Immediately below the dam lies a narrow gorge, a natural funnel, a channel capable of concentrating enormous amounts of water into a relatively confined space. Communities closest to the dam would have very little time to react. In some modeled scenarios, the first flood surge could arrive within minutes, not hours. Minutes. Further downstream, the flood wave would continue expanding as it moved through Zambia, Zimbabwe, and eventually Mozambique. Roads could be cut off, bridges could be destroyed, communications could fail. Emergency response systems would face enormous pressure. Then comes the second concern, Cahora Bassa. Located further downstream in Mozambique, Cahora Bassa is one of Africa's largest hydroelectric dams. Under normal conditions, it is an engineering achievement in its own right. But in a major Kariba failure scenario, engineers have long studied whether the incoming flood wave could exceed the system's ability to safely manage the surge. The exact outcome would depend on countless variables: reservoir levels, failure mechanisms, weather conditions, response measures. But one thing remains clear: the consequences would not stop at Kariba. They would travel hundreds of kilometers beyond it. Some risk assessments have estimated that more than 3 million people live within areas that could experience some degree of impact under an extreme dam break scenario. 3 countries, countless communities, one river system connecting them all. And yet, this is where the story takes an important turn, because despite all the alarming simulations, despite the warnings, despite the headlines, Kariba has not failed. Engineers continue monitoring it every day. Rehabilitation projects continue. Sensors continue transmitting data. Inspections continue. Repairs continue. The future of Kariba is not a story that has already been written. It is a story still unfolding. And that may be the most important fact of all. Because the purpose of studying disasters is not to predict them, it is to prevent them. Kariba stands today because generations of engineers have identified problems before they became catastrophes. The question now is whether those efforts will be enough for the next 60 years. Kariba was built to prove what humanity could achieve. Today, it reminds us of something equally important. Every engineering miracle has a lifespan. Every solution creates new challenges, and every generation inherits the responsibility to maintain what previous generations built. For now, Kariba still stands. The turbines still spin. The lights still turn on. But beneath the surface, the race continues.